Welcome back to this video series where I continue to talk about content contained in the book Introduction to Nonlinear Control. And in particular, in this video, I'm going to talk about optimal control. So here we start with a couple of definitions and define the corresponding setting. So we look here first at continuous time nonlinear dynamical systems with state X and input U. And then to introduce the concept of optimal control, we will additionally look at cost functions or cost functionals, which specify a particular performance criterion, which are defined through particular running costs L, integrating the running costs from 0 to infinity, and then returning the corresponding cost functional depending on a selected input U and on the initial condition. With the cost functional, we can define the optimal value function, which is just the minimum value when we minimize the cost functional over the possible input trajectories, subject to our dynamics and subject to our initial condition. So here, as quantities we're interested in, we have the optimal value function v of x0, and additionally we are interested in the optimal input trajectory. So which input u star gives us the optimal value function. And what we would actually like to have is a feedback law. So we would hope that the optimal input trajectory can be characterized through a feedback law, meaning that mu of x star of t can be written as u of star of t, which then define for us an optimal solution pair, meaning x star being the optimal solution and u star being the corresponding optimal open loop input. And what we can also observe here is that under specific conditions, x star is uniquely defined through u star and the initial condition. As an example, so what we can look at here is a linear system. So x dot is equal to ax plus bu. Then what is usually done is to take a quadratic cost function defined through positive matrices Q and R, and to define the corresponding cost functional through this quadratic cost functional here by penalizing or calculating the value corresponding to x with respect to q and the input u weighted by this matrix R. So what we want to solve is this optimization problem here, or the corresponding optimization problem here, returning us either the optimal value function for a given initial condition x0, or giving us the optimal input for a given initial condition. However, in general, it is not possible to solve these optimization problems. So for general nonlinear systems and for general running costs, these optimization problems are usually intractable. For the special case of linear systems and quadratic costs, one can solve these optimization problems explicitly. So that's the well-known case of the linear quadratic regulator, where again we take the linear system dynamics and the quadratic cost functional. Then the following theorem can be stated, where if we take positive definite matrices Q and R, then the statement is that if there exists a positive definite matrix P satisfying the so-called algebraic Riccati equation stated over here, and if this matrix here is Hurwitz, Hurwitz giving us a criterion stating that the underlying system is asymptotically stable, then in this particular case, the optimal feedback law can be written in this way. So as in particular kind of this component here of this Hurwitz matrix, and the optimal value function is a quadratic function with characterized through this positive definite matrix P coming from the algebraic Riccati equation. And yeah, this is also then a Lyapunov function of the closed loop system, meaning this function V here can be interpreted as a Lyapunov function. This was the case for continuous time systems. The same statements can be made in the discrete time setting, where the only thing we have to replace is the integral going from 0 to infinity with a sum going from k equal to 0 to infinity, and of course replacing the continuous time argument t with the discrete time argument k here. But the remaining definitions as shown over here remain the same. And there is then also a corresponding results for the discrete time setting and the linear quadratic regulator, meaning again, for the particular case of linear dynamics and quadratic costs, we are able to calculate the optimal value function and the optimal open loop feedback law, or even get a characterization of the corresponding feedback law instead of an open loop solution through now the discrete time algebraic Riccati equation, looking slightly more complicated, but structurally is the same. And here we also need to look at this matrix to check if we have asymptotic stability, namely this matrix, looking at the discrete time setting, needs to be a Schur matrix instead of being a Hurwitz matrix. But again, here in this second component, we obtain a characterization of the optimal feedback law, which allows us to write mu of x through this matrix here, which we also recover over here. And again, the optimal value function is a quadratic function characterized through the optimal solution of the algebraic Riccati equation. Okay, so in general, that's nice. For a specific setting, we can set up an optimal control problem through an optimization problem. And in the case of linear dynamics quadratic costs, we can solve that optimization problem explicitly to get a closed form solution. What we need to keep in mind is that the optimal solution pair, meaning the solution X and the optimal open loop input U star, is only optimal with respect to a specific measure, namely with respect to the particular cost function. In the case of the linear example, with respect to the selection of Q and R. So the selection of Q and R needs to be well justified. And, well, as already kind of indicated, to be able to obtain this optimal solution pair here, we need to be able to solve an infinite dimensional optimization problem in the continuous time setting as well as in the discrete time setting, since we need to be able to find this functional U star of k or U star of t. So this means that we will only be able, or if you look at textbooks, you only find explicit solutions for very specific settings, for example, for linear dynamics. Moreover, in most of the cases, we only get open loop solutions, but not feedback laws. So meaning we get u star of t, but we won't get mu of x of t, so a feedback law to get robustness of controllers if they are implemented on a real-world example. So questions that remain after looking at these initial optimal control problems are how to obtain results that can be extended also for nonlinear systems, how to incorporate state and input constraints, and how to simplify the setting so that we go from an infinite dimensional optimization problem to a finite dimensional optimization problem to obtain tractable problems for more general settings. And one way to get there, to get more tractable an optimization problem that might be tractable for more complicated dynamics, is to make use of the principle of optimality. So principle of optimality, written in words here and then graphically visualized on the right. So the principle of optimality says that for any point on an optimal solution, x star of t, the remaining control inputs u star of t are also optimal. So if we look at the setting over here, if I have an initial condition here and I want to reach the origin, so I have here denoted my optimal solution x star depending on x0, then if I take any point on that trajectory, so for example x star at time capital T, then I can look at the corresponding optimal solution starting from this point here, which would then mean that I'm having x star of t when initialized now at this new point. And then the corresponding solution here from 0 to infinity and from t to infinity coincide. So let's make that more precise using rigorous arguments. So assume that solutions of the optimal control problem we are looking at are unique. Then if we take an initial condition and let x star u star be the corresponding optimal solution problem of the optimization problem we have looked at before, meaning we want to minimize the cost function subject to dynamics and initial condition, then we can take any arbitrary capital T larger than 0 and now look at the solution x bar of x star where we have changed the initial condition here. So now it's the optimal solution at time t, and then look at the corresponding optimal control problem and solve now the optimal control problem with respect to that new initial condition. Then what we get is that the solutions coincide, meaning if I'm changing the initial condition here, that's equivalent to changing the time argument and shifting time argument correspondingly with respect to the input as well as the solution. In the case that we don't have unique optimal solutions, then the statement is not true in the same way. Then only equality of the optimal value function or the cost function is guaranteed, meaning if I evaluate my cost function at x star or this shifted x star, then I get the same value, but not even though the solutions might be different. In a discrete time setting, I can get a similar result, and here also potentially a different characterization or visualization of the principle of optimality. So here is a different visualization of the concept where let's assume I want to find the cheapest path going from A to E, and going from A to B costs 10, going from B to C costs 5, and then from C to E costs 3. And I could alternatively go from B to D and then from D to E. Here, since this is a simple example, we can calculate that from A to E, the cheapest path is going from A to B to C to E. So then if I ask the question, what is the cheapest path to go from B to E? Well, then it also needs to contain this component of the optimal solution from before, and giving the same representation here, that the tail, meaning the tail of the overall optimal solution, is again optimal here. Okay, how can we use that now? So we can use that principle of optimality to incorporate input constraints, for example. So let's start with the discrete time setting, taking a discrete time system and a corresponding cost functional, here on the example of, again, quadratic costs. But now the change we're going to make is that we assume that our input is constrained, meaning U for all K needs to be in a compact closed convex set, or sorry, just closed and convex, doesn't necessarily need to be compact. And then we can look at the corresponding optimal control problem, where now the only difference is that we have the constraints here as well. So U of K needs to satisfy additional conditions. How do we solve that problem? Well, what we could do is we could simply apply the unconstrained results, or previous, on a couple of slides ago, we have seen a solution for the discrete time linear optimal, the linear regulator problem, which told us that our optimal feedback law for the unconstrained setting can be written in this form, meaning we have a linear feedback law characterized through these matrices here, which we can summarize in K, and our optimal value function was a quadratic function characterized through a matrix P as a solution of the discrete time algebraic Riccati equation. We also know that in this case then this V here is a Lyapunov function, which gives us asymptotic stability properties. So if that's the case, then we can look at the closed loop dynamics. X plus is equal to A plus BK. And we can define set XF as the sublevel set, as an arbitrary sublevel set of the Lyapunov function, so V of X less or equal to Z. And that set is forward invariant for all C, but we will select a particular C now. Namely, we select C in such a way that K of X is contained in these constraint sets U here, for all X satisfying the Lyapunov sublevel set inequality here. We then know is that the origin 0 is locally asymptotically stable with Bazin-of attraction containing the set XF. And in that set XF, we also satisfy the constraints on the input U. So as a next step, we are now going to apply the principle of optimality. And we need to rely on another assumption here, namely we assume that for all X in Rn there exists an input U from this constraint set, such that we can render the origin globally asymptotically stable. With that, well, we know that for all x0 in Rn, there exists an n in n, so n just needs to be large enough such that xk will be in this terminal set xf here. And that then, once we are in this terminal set, then forward invariance is telling us that we will stay there for all k in n. And under this assumption that xn is contained in the set xf, we can look again at our optimal control problem here and at the minimization problem, which we can write as the sum now over the optimal values. For simplicity here we have removed the time argument. And then I have this sum here from 0 to infinity, which I can simply split going from 0 to n minus 1 and then from k equal to n to infinity. So the step we've taken here is simply splitting the sum into two components. And then what we know is that this red part here, we already have a solution. Namely, there we know that the optimal costs there are represented by x transpose pfx, meaning we can replace the red part by the optimal value function with respect to this new initial condition. So then we have rewritten this the infinite sum here from 0 to infinity as a sum from 0 to n minus 1 plus this additional component from the unconstrained setting. So if we now summarize these results, if we restrict the definition of our input to a finite series, so un being defined from 0 to n minus 1, and all of these components uk need to be in u, then we can also look at this now cost function, the only new component being that we are looking at this index n here, so we have replaced infinity here in the sum by n minus 1. Then we can continue to rewrite the optimal control problem from the previous slide, where we started with the cost function now without the index n, meaning that's the from 0 to infinity. But with the derivations from the previous slide, we can rewrite that now as an optimization problem, only optimizing the first components and having these terminal costs here, giving us the costs to drive the state xn to 0 once we have reached the set xf. So in particular, instead of the original optimization problem here, we can look at this optimal control problem down here, where now we have rewritten the infinite dimensional optimal control problem or infinite dimensional optimization problem into a finite dimensional optimization problem. And the optimal open loop input in this case then is given by these optimal components from 0 to n minus 1, and the remaining components are simply given through k times x star. So here we can use the components of the unconstrained setting. What we need to keep in mind here is that u star and v star are only implicitly known as the solution of this optimization problem here, and also the equivalence of this optimization problem here and the optimization problem here, where again this optimizes u0 to u infinity, where this optimizes u0 to un minus 1. This equivalence here needs to be looked at with caution, because it assumes this non-trivial assumption that xn star is contained in this sublevel set of the Lyapunov function. If that is guaranteed, if we can guarantee that, then it's fine, but in general it's also not easy to guarantee that. Alternatively, one could consider terminal constraints and enforce this condition here by considering also the constraint that xn needs to be in xf. However, also in this case is problematic, because in this case we might actually not be able to reach xf in n steps. So n needs to be selected large enough that that is guaranteed. If we select n too small, it might be that it is not optimal to reach xf in n steps, but potentially in n plus 10 steps, meaning we only get a suboptimal solution because we try to enforce that we reach this set too early. But nevertheless, the takeaway here is that if we want to solve optimal control problems, meaning taking cost functions into account in the controller design, then this is in general a difficult problem to solve, because the problem we started with is an infinite dimensional problem to be solved to obtain the solution of the optimal input and the optimal value function. While there are some solutions for some settings, meaning linear systems and quadratic costs, for more general settings that's not the case, and there are only limited approaches for nonlinear systems or non-quadratic costs. So what we did was to rewrite the optimization problem into a finite dimensional optimization problem, making use of the principle of optimality to get a tractable problem to be solved. And this will be extended then in the next chapter and in the next presentation in the context of model predictive control. With this, I want to conclude the presentation here, and as mentioned, then talk about model predictive control